eyes off them, not even for a second.
For my next demo, I'm going to need some magic. Change color, change color, change color, change color.
For the next demonstration, I'm going to need a volunteer. Everybody ready?
Chemistry's awesome.
It's time for fire!
Welcome to the Carleton University Chemistry Magic Show! To the 15th annual Carleton University Chemistry Magic Show. Okay, can we get the lights back up? Okay, so my name is Jeff Manthorpe. I'm a professor here in the chemistry department. And on my left, I have one of our staff members, Aaron McConnell, who is also going to be helping me out today. And I hope everybody's having a good time so far and you like that first demonstration. So I want to show you quickly what that's all about. And so in math class, you've probably done something about area, measuring the area of different geometric shapes. And surface area can be important if we're talking about the chemical reaction of a solid. And oh, thank you. This is why I have Erin here, because she remembers the things I forget. And what I have in my hand is a powder. Oh, it's a very fine powder called lycopodium. And as you can see, it just kind of chars, and it's actually still burning in my hand. Fortunately, I've got a pretty significant amount there, so it's not really getting too hot. But clearly, that's not as spectacular as what I did before. Now, that's because the area of the powder that was exposed to air was very small. But when I blow through the tube, the particles get spread out and mixed with air so that the air can get access to a much larger amount of the surface area of the particles. So now, everybody loves that one, so let's do that one more time. Maybe we can get the lights off again. And meanwhile, I'll load this up. Okay, here we go. 10, 9, 8, 7, 6, 5, 4, 3, 2, 1. All right. And that's reason number one that we get the fire alarms turned off for this show. Okay, Erin, over to you.
Great, excellent. So we're going to learn a little bit about acids and bases. So acids and bases are two types of chemicals. And so in solution here, we have multiple different things called pH indicators. And so if you think of an acid is something that's like lemon juice or orange juice or something that gives you kind of that like tangy taste when you eat it. A base is something that's like laundry detergent or soap, something that's kind of slippery, these sorts of properties. And so we can actually change the properties of a solution. So here we have these multiple solutions to make it more acidic or more basic. And when we put in something called a pH indicator, this will tell us just by the color whether something is acidic or basic. So to change the pH, we could do a few different things. So we could breathe into the solution because what we're breathing out, CO2, is acidic. But we also have a special kind of ice called dry ice, which is the same chemical. So the CO2 that's going to make our solution acidic. So when we drop it in, you'll see, watch carefully and see what happens to the solution. So this one, if you caught it, there was a sharp transition from pink to yellow. So let's see what color this one's going to change from. So this one is purple. You can see it changing. This one's a little bit slower. Sometimes we have different amounts of the indicator and different amounts of acids and bases, so it can take a little bit longer, or it can need a little bit more of our CO2, our dry ice. So we'll put that in there and we'll see what it gets to. All right, so you can see it kind of went from like a blue to a green, kind of green-brown. So let's see what happens with this one. You might also notice that something else is happening here. So here we have a gas that's coming up, bubbling up from the CO2 pellets and forming this gas, and it's heavier than air. So you'll see it falling over the solution and falling to the ground. So this one is changing from orange to red. So the first one, if you remember, it was pink and it turned yellow. So we have another pink indicator, and take a guess and think what color it's going to change. Let's see. So this one went from pink to clear. So sometimes we have chemicals that look like they're the same because they're giving us the same color in solution, but they're slightly different and we get slightly different properties. So this last one is a special indicator. It's called a universal indicator. So if you have something like universal headphones or universal remote, you know that it works with lots of different things. So it's the same idea with our universal indicator. It works with lots of different pHs. So we're going to see, you have to watch this one carefully because it's going to transition or change from multiple or through multiple different colors. So let's watch and see what we can see. So it starts out as blue. Now it's green, yellow, orange. Can't really see it on the camera very well, but it's orange here. And if we add a little bit more, sometimes the pellets don't dissolve fast enough. So we'll add a little bit of acid directly in, and we'll see if we can get it to change a little bit more. Oh, there we go. And we took it from orange to red. So on camera, it looks kind of orange, right? So we changed it a little bit more. So we'll come back. Remember this idea about this carbon dioxide gas being heavier than air and vapor, because we're going to do something with that later. So keep that in your brain. All right.
Okay. And now over here, I have 3 colorless solutions. Okay, and this is a holiday show, right? So we ought to, do some holiday-themed demonstrations. So I'm going to do, this one's going to be for probably the last holiday we had, although technically it's not a holiday in the sense that we get the day off school. But it's a pretty popular day, don't you think?
I think a lot of people, it's their favorite holiday.
Yeah, it's their favorite holiday, right? So this is what we call the Halloween reaction. So if we're going to do a reaction called the Halloween reaction, right, we're going to have to make 2 different colors, right? We're going to have to make orange and black. Okay, so watch what happens. Orange. And black. All right, so that's actually a reaction where we produce an orange compound called mercury iodide, and it's actually not very soluble in water, so that's why it sort of gets very opaque, so you can't see through it. And then what we get is something called a starch iodide complex, which gives us this very dark blue, almost black color, and that actually has numerous applications in chemistry and biology. So that's a great demonstration, but it actually combines a couple different things that are separately probably have a little more direct purpose for science.
That's right.
Well, though that's still my favorite use of them. Okay, back to you, Erin.
Excellent. So just to start, the next demo that we're going to do, remember I told you about how this CO2 is heavier than air. So in this, we have some candles lit. Can we maybe get the lights turned down for this? So what I'm going to do is I'm going to use this gas that's coming off of these CO2 pellets to extinguish this flame. And so we'll get the lights turned down. Oh, perfect. Excellent. And so now in this cooler, I have dry ice. Yeah, you can't see on the video, but it does smell a little burny in here.
I can't imagine why.
As long as it's not us that's burning, and it's just our science. So you'll see there that we've extinguished all of our candles, all of our flames, and that's because all of the air that was in this that we were able to breathe with oxygen in here has been displaced, or it was pushed out by the gas, and that extinguished our flame. So our next demo is one of my favorites. I think it's probably one of everyone's favorites, and you may have heard of it, or you may have even tried it yourself. This one is called elephant's toothpaste. And so to do the elephant's toothpaste demo, at home you may have used something like yeast or hydrogen peroxide as part of your reaction. And so we're going to do a very similar reaction here, except we're going to use something called potassium iodide. So where yeast is like a little organism that is changing the hydrogen peroxide solution that we're using into something called water and gas, the potassium iodide can do that much faster. So we're going to see, hopefully, a bigger and faster reaction than you would see from doing it at home. So first we add the potassium iodide. That's what you saw me adding. It's just a white powder. It doesn't look like anything special. Then we're going to put soap inside. And so if you've done this demo before, you'll know that the soap is important. We need that in there. And you'll see why in a minute. Then, because it's elephant's toothpaste, we need to add some fun colors in here so we can see what reactions are taking place. So the color isn't actually part of the reaction, but it lets us monitor it and see what gets created. So I like to add blue and red because it's kind of like minty fresh toothpaste. So now we're going to add our hydrogen peroxide. So the hydrogen peroxide that we have in the lab is also much, much stronger than the hydrogen peroxide that you can buy at home or at the grocery store or the pharmacy. And so that also makes the reaction happen faster. So if you want to try this at home, you can do it. You can also buy slightly stronger hydrogen peroxide at like a beauty store for hair dye. All right, so we're going to keep a close eye on this so you don't miss it. And we'll see what happens. So you'll see that this very quickly becomes a big mess. And you'll notice that there's water vapor coming off of, or steam coming off of the foam. And what's happening here is the hydrogen peroxide is actually becoming water and hydrogen gas and oxygen gas. So you're seeing all of this boil off, and we have to use the soap. Remember I said it was important? We use that to trap the air that's coming off, the gases coming off of the reaction, so it gets all trapped, it makes all these bubbles, and it shoots out of the flask. Grace.
Okay, time for another favorite. So here I have another beaker of some chemical dissolved in water. Okay, this is actually containing a long stringy molecules called polyvinyl alcohol. Okay, and you might have encountered polyvinyl alcohol in things like detergent pods. So the actual coating on the pod is actually made of polyvinyl alcohol, and as you can tell, it dissolves in water. Now, what we're going to do, because these are long, stringy molecules, we can actually make them interact with each other by adding what we call a cross-linker. And so when we do that, it's like each of these molecules of spaghetti gets attached to another one, and the whole thing becomes stiffer. So what I'm going to use is our cross-linker. Oh, and if we're going to make slime, I mean, we got to make it green, right? Stir that up with a little green food coloring. Okay, and now our cross-linker that I'm going to use is borax in water, and borax is a household laundry detergent. So you can do this at home with glue, wood glue, and just white glue and borax. Whoa. So you can see that's getting pretty gooey. I think we might be able to do better than that. Let's see. Add a little bit more. you can see that we're, there we go. That's more like it. So that's some really good slime. All right. Achoo!
Oh, gross.
Okay. On that pleasant note, back to you, Aaron.
Great. Okay, so we're going to come over here, and we're going to show you this reaction. You're going to be able to look at it right from above. Perfect. So we're starting out with, this is just water. Keep an eye on it, though, because we may have an indicator in it, because in our reaction, we may have another pH change. So we're starting out with elemental sodium. So this is just sodium. You may have heard of sodium as like sodium chloride, or we talk about having a lot of salt in our food. That's often sodium chloride. That's a different type of molecule than what we have right here. This is just sodium. And sodium, like this, likes to react with water. So water is what we have in this reaction here. And so I'm going to take out a little bit of this metal so that you can see what it looks like and see how it kind of reacts here. So what we have the metal stored in, it looks like water, but it's not. It's oil. And the oil keeps it safe from reacting with any water that could be in the air because it's so reactive with water. So you can look that it's very soft. I just stuck the knife in it, and we can see that we can pick it up that way. So we're going to wipe the oil off here. And you'll see, perfect, that we can actually cut it. It's so soft we can cut it with a knife. And when we do cut it, you can see it's quite shiny on the inside. So it kind of looks like we would expect a metal to look like, but we don't necessarily expect that when we throw metal into water, something exciting might happen. So this is a special property of sodium, and let's see what happens. So I'll cut a couple of pieces. And it's super important that as scientists we're safe, so we're going to put the big piece back into the jar. And we're going to put it out of the way here. Okay, so the oil is really good at protecting, so we need to make sure that we get it off really well so that we can see the cool reaction that's about to take place. All right, friends, are you ready? Okay, so make sure you're watching the color as well. This one we can actually hear too. You can see the little ball flying around in there. That's our metal. It's reacting. The sodium is reacting with the water, and it's producing something called sodium hydroxide, which is making the pH of the solution change, or the properties of the solution change, and so we end up with this pink color. The indicator tells us that the pH has changed. So that is a really cool, one of my favorite. Did you hear that pop? That's how reactive the sodium is. So let's watch it again, because it's fun. Okay, let's see if this one goes any faster. So you'll see that again. You can see the, maybe we can show the side because it's really smoky on the top. There we go. This one's thinking about it. You can hear it. I don't know if we're going to get a flame with this one. There may have been a little bit too much oil on it. Oh, got just a little one. There we go. Perfect. And that's the end.
Okay. So I have another demonstration over here that involves sodium. So as Aaron mentioned, you may have heard of sodium as part of salt in our food. And this demonstration actually involves basically salt and vinegar chips. So what we're going to do here is we're going to not eat any chips, unfortunately.
Oh, darn. What about French fries?
I wish. So if you like salt and vinegar chips, this is what's on your salt and vinegar chips. Okay, the sodium part gives us the salty flavor, and then the acetate part is actually what's part of vinegar and gives us that acidic vinegar taste. And so what I have here in this in these flasks is a solution of sodium acetate in water. Okay, now this is actually what's called a supersaturated solution. So there's more sodium acetate dissolved in here than it really should be able to dissolve. And so as a result of that, if we add even the tiniest bit more, it will all come right back out. And that's actually also releasing a nice little bit of heat. And so sometimes it's reactions like this, salts dissolving or coming out of solution, in fact, either way, depends on the situation, can actually release a fair bit of heat and create some of those hot packs that we sometimes use. Okay, now there's another way I can show this demonstration that's also a lot of fun. So I have a little bit of sodium acetate in the dish here, and I'm just going to pour this out on top. And now as I pour, you can see that it crystallizes faster than it runs down the side of the tower that we're making here. And this is the process that happens in caves where we see stalagmites and stalactites. Stalactites, this happens as it drips off the top of the cave, the roof, and stalagmites, it crystallizes out when it lands on the bottom. So there we go. We've made our own stalagmite. Okay, and I think I'm going over to this one, right?
Sure, you can do that next.
Yeah. Is that what's actually next?
Yeah, and then I'll do the Geiger counter after.
Okay. So if you're paying attention, you've noticed that this has changed. Okay. This flask here used to be blue. Okay. It contains a dye called methylene blue. And I like this demonstration because it allows me to get my frustrations out. So what I have in here actually causes the dye to lose its color. And it's called a reducing agent, which is the opposite of oxidizing. And so when things oxidize, probably one of the most common oxidation processes you've seen is metal things rusting. So that's when iron metal starts to turn to iron oxide. Now, I'm going to oxidize this dye just by shaking it. And so what it's doing is it's being oxidized by oxygen in the air inside the flask. And you can see that there's still some of the reducing agent in the flask so that it immediately starts to dissipate the color. But if I can shake it up again, give it a really good shake, goes this nice dark blue. And now it'll take a little bit longer, but it'll still fade out. And I can do this for about half an hour. Well, the dye can do it for about half an hour. My arms can't. Abracadabra, color disappearo. Hurry up, hurry up, hurry up. It's going. It's winter. Everything's slower in the winter.
It's thinking about it.
Yep.
All right.
Okay.
Should we come back to that one?
Yeah, it'll probably be fine in about 10 seconds. As soon as we turn our backs, it'll change color, right?
Right.
Yeah. Okay.
Oh yeah, you can see it.
Yeah.
Great. So like Jeff has shown, and I've shown with the pH indicators, there's kind of multiple ways to know when a chemical or a physical reaction is happening. So one of the ways is color. So we've seen multiple different indicators of color. One of the ways is we see energy generated. So we've seen fire, a few times. One of the ways we can tell that something is happening, or we can tell something about a chemical, is by sound. And the chemical itself is sometimes making a sound, so we heard with the sodium, but sometimes we use a special device to tell us what sort of chemical there is. And so in this case, we're using something called a Geiger counter. And a Geiger counter is something that measures radioactivity. So when we turn it on, you'll hear it start to tick, because just all around us, there's some amount of radioactivity or energy. You may have heard the word radioactivity if you've done a medical test. So they use this in medicine to help look at your body on the inside. But we can also use it in chemistry to tell us whether certain molecules are safe to use. So if something is radioactive, it can be dangerous. The type of radioactivity we're going to learn about today isn't dangerous for us, certainly not dangerous for you because you're far away. But what you'll see is when we come close to this molecule, or this chemical rather, that is radioactive, even around the jar, we start to hear a little bit more of those ticks. So that's because we're getting closer and closer. This far away, we don't hear it. This close, we do. And when I open it, let's see what happens when we put the counter right on top. So you hear that? Do you hear how quickly and how intense that reacts? So let's hear it again. So that is something that has been used for a very long time. Do you know when the Geiger counter first started being used?
I can't remember, but I do remember that at one point, I think it was Geiger's great-great-grandson or great-grandson was actually a student in first-year chemistry.
Oh,
here.
That's cool. That's awesome. Yeah. So this is a really cool tool. It helps us be really safe because the type of chemistry we use that uses radioactivity can be dangerous. And so that's just an awesome demonstration. Not everyone gets to see those kind of working in real life. So I'm glad we could share it with you. All right, Jeff, back to you.
Okay. All right, and as you can see, demonstration, a little bit slow, but did ultimately cooperate. And now give another quick shake. Okay. And speaking of colors, let's do another holiday-themed demonstration. So, 3 colors that we may expect to see associated with the Christmas season. How about silver? In this case, it's not actually silver, it's a silver color. That's actually mercury, which is incredibly dense. So that amount that I poured in there probably weighs about 400 grams. And now on top of that, I'm going to pour in a little bit of a green compound in water. So that's actually a salt, nickel chloride. And on top of that, I'm going to pour in a red dye that's dissolved in an oil-based solvent. So we're going to have a bit of a salad dressing situation here. And so this is a red dye called Sudan 3. And so we've got 3 nice layers there. Okay, and now I can actually shake this up. And we can see that the layers actually don't mix. They actually separate back out. And there we've got our silver, green, and red. The green isn't quite as bright a green as it was because it's got a little bit of the red sort of suspended in it. And it may be reacting a little bit with the mercury too. But there we go. 3 layers. This is our Christmas demo.
Great.
Okay.
All right. So speaking of winter time and holidays, we're going to do another demo that's very cold. So we're going to come over here. This is our liquid nitrogen demo. So liquid nitrogen, like I said, it's very, very cold. So do you have any guesses at how cold it might be? Anybody? Just you can shout them out in your class. What about around here? Jeff, how cold do you think liquid nitrogen is?
Too cold. I
Too
hope
cold.
it never gets that cold outside, because then all the air would start to liquefy.
That is right. It is very, very cold. It's minus 190, 172.
196.
196, minus 196. So it's very cold. None of us have ever experienced that cold because we would be popsicles. So you can see that there's a little bit of vapor coming off of that. That's a little bit of gas and kind of water and stuff. And so we can actually pour our liquid nitrogen. You can hear that. And the sound that you're hearing is actually relative to the room that we're in, the temperature. The liquid nitrogen is so cold and the room is so warm that it's boiling. So you're hearing that bubbling going on. So what we're going to do is we're going to think about liquid nitrogen in a way that maybe you've seen in kind of like science fiction movies. So there's this idea of cryogenics. So cryogenics is the idea that maybe you can freeze a body if it is very sick. So say you have a disease that's incurable. Maybe we can freeze your body, and then when science discovers a cure for you, we can unfreeze your body and see if we can cure you at that time. So we're not going to freeze any bodies, but what we are going to freeze is some lettuce, because even though this lettuce doesn't look like a human, it has a lot of properties that are similar. So lettuce is mostly water. You can see all those veins in there. And the water is being carried through the plant in that way. And so we're going to see what happens when we put something that is mostly water, like we are, into liquid nitrogen and see if we can keep it kind of safe. So we're going to put it in, and you'll hear again. So now imagine we're super excited. We found a cure. We're rushing you through the facility to take you, and we see what happens, and oh no, we hit a wall, and now you are cracked, and just cracking in my hand. So what do you think? What's your hypothesis as a scientist if you're asking a research question? What do you think would happen if we froze a human and then tried to unfreeze them? Do you think it would help? It would last? So maybe if we were more gentle. So let's try another piece and see. We'll freeze it and we'll place it very, very gently, and we'll see what happens. Once it defrosts, if it's going to look like nice, healthy lettuce. So we know lettuce it's crisp. It has this nice kind of, oh, see, it's already cracking when I took it out. So let's just set it there and see what happens. One thing that's also cool about liquid nitrogen, and if you've learned about plants and plant cells and stuff in school already, then you might know that everything that's living is made up of cells, right? And so when we break those cells, it releases the chemicals that are responsible for smell. And we can really, really smell intense lemon because we've burst all those cells open. So that's something that's cool. So you could probably even try that at home, put it in your snowbank and see, it might be smelly. But we have some other things. We're going to talk about what happens to a gas when we put it into cold, okay? So we have a closed container. So these are our balloons. They're closed. We have gas. It's a mixture of gas because I was breathing it out. And we're going to put this container in liquid nitrogen and see what happens. Yeah, let's do that. So let's move over here. Okay, so again, what is our research question? What's our hypothesis? So what do you think? We're going to put these containers of gas, and then we have some other containers of gas, just a different shape. And we're going to put these into our liquid nitrogen, and we're going to see what happens. So in your class, you can shout it out, take a guess what you think might happen, and let's see. So we'll start out, we're going to put this one in, and let's watch. can you see? You might be able to hear. So what is happening there? So as gas becomes cooler, it takes up less and less space. So the container that it's in is shrinking because we had to stretch it to add the gas in there. So let's see how many things we can put in here. Do you know where the tongs are?
I had them out with the sodium.
They might be on the, oh yeah, they're on top of the cooler there. Okay, so let's see. So we squished, thank you. That's three balloons now. So 2 little ones and 1 big one. Let's see what else we can get in there. So we have to use the tongs because my fingers are mostly water. So if I just keep holding the balloons, I'll freeze first my glove and then my finger. Let's see, we have this one, and we have one more. We'll see if we can get them all in there. What do you think is going to happen? Are we running out of space? I don't know. I think I'm just running out of bravery of getting my fingers cold. And you see how quickly it becomes very, very soft. And you'll see it starts to pucker in these places. So it's freezing there. Okay, so now that we've got these in here, what do you think is going to happen when we take them out? So we know that if gas gets cold, it shrinks. So what do you think is going to happen if gas gets warm? Let's test your hypotheses. So we'll take one of these guys out and see what happens. Just a warning, sometimes they pop. So we got one. Oh, this one was good and crispy. Let's see. Looks like a pancake. So you'll notice that they're all coming back, and they come back pretty quickly. They're going to warm up pretty quick. And you can hear the ice breaking while it warms back up. So we'll see we recovered our balloons pretty well. Let's see about these little ones.
Have you ever tried this with balloon animals?
Yeah, I did once, and they all popped because they had all the twists in them.
Yeah.
That's a great question because I'm sure some people were wondering. We did try this with balloon animals, like Jeff asked, and because of all the twists and turns, the pressure when they were warming back up popped them.
That's too bad.
This guy's thinking about popping, but maybe we're okay. All right, great. Let's just go back, before we move on, let's go back to that other piece of lettuce and see what it looks like compared to a fresh, healthy piece. Okay, so we have our fresh, healthy lettuce. It's teeny tiny, but you can see that it's still very crisp. It's standing up straight. The leaf is maintaining its shape. Whereas if we compare that to our frozen lettuce, what do you think? So our idea of cryogenics, I don't know that we're there yet in science. I don't think we are. But maybe in the future, maybe we'll find a better way. But for now, we can say that no, we and things that are mostly water are not going to do very well in liquid nitrogen. Great, so over to you, Jeff.
Okay, can we get the lights off, please? And now it's time for a demonstration you can try at home. Okay, so here I've just lit a candle. Okay, and this is one you can do to really freak out your friends and family over the holidays. It's a delicious demo. So yeah, we don't have the lights totally dark in here, but hopefully you can see this bottom part that I was eating was actually, still is, a banana. Now, what I put on top, continuing with our food theme after the lettuce.
Yeah, this is the part of the show where Jeff gets hungry. So
Yeah.
we have lots of snacks.
So what we have right here is a pecan. Here, maybe we can even just zoom in on that. So that's just a plain old pecan nut. So clearly don't try this at home if you have a nut allergy. But nuts contain a lot of oil. And that oil can burn. So you may want to get some help from, an adult, and make sure you have very steady hands. But now we can light that. That'll burn for a few minutes.
You can also light it with a barbecue lighter like we've been using. It's just not as fast. You
Yeah.
have to be more patient like
Yeah,
Jeff was
you don't
saying.
need a blowtorch.
Yeah,
Yeah,
we
you-
just use one for fun.
Yeah, and expedience. Okay, and then with the lights off, yeah, sure, it looks like a candle. You could even put it on a really waxy candlestick, and then just blow it out. And the roasted nut mixed with the cool banana. You don't really burn your mouth. And we can go on to our next demo. Now we have to go back to the dark, right?
Yep, we're in the dark for the rest of the show.
Okay. So, time to get our whites whiter and our colors brighter with laundry soap. Now, I'm just going to put a little bit in a beaker here, and I'll show you. Okay. Once we get the lights back out again. Our poor cameraman is getting his exercise. Oh, and they came back on. There we go. Okay, so here's some plain old liquid laundry detergent. And underneath it here, I just have a UV light or a black light. Okay, so what's in here is a compound called umbelliferone, which actually small amounts of this will stay in your clothing and help make it brighter, because it actually takes the UV light and then gives it off as blue light. So it actually does make colors look brighter. It also makes whites look whiter, because white fabric tends to yellow as it gets older and it ages. And so the blue color that's being emitted there actually helps counteract the yellowing and actually makes it look white. Okay. Yeah.
Great. So we have a
we're
similar.
going to move this over, right?
Oh yeah, there we go. We have a similar kind of chemical in something that you might be familiar with. You might use these at school. So you might recognize these. They kind of look like glow sticks, but now that we have our zoomed in, you'll recognize them as highlighters, right? So they're called fluorescent highlighters because they have this property of being able to fluoresce or to release light that they've absorbed. And so we've drawn a picture here, a message, and we'll see if you can read it. So we've done it in different colors as a bit of an experiment. So you can definitely read happy. Underneath it says holidays, and we wrote it in blue. So the blue one, there we go. The blue one is not as fluorescent, but you can see definitely in our experiment that the yellow, the green, the orange, and the pink are fluorescent molecules. Great.
Okay, and one other thing, let's get back to food. Okay, what I have in here is tonic water, and it contains a molecule called quinine, which was actually one of the first, probably the first, really effective treatment for malaria. So it's a mosquito-borne illness that's killed millions of humans throughout human history. But now we have very good treatments for it. But it's still an issue because sometimes it's difficult to get the medicine to the people who need it. But quinine actually fluoresces under UV light. So what that means is it absorbs the UV light and then gives off blue. Okay, and just to show you that I haven't really done anything, to this to kind of cheat, I'll just
Now, this is the part of the show where Jeff gets thirsty.
Okay. All right. So, how are my teeth?
Pearly white.
Okay. All right. What are we doing now? Oh, yes, that one.
I can hold it today if you want.
Okay, sure.
So, we have to turn this off, though.
Yep. Okay. So up next, we're going to talk about a related phenomenon called phosphorescence.
Where is this? I'm trying to figure
So
out where it's.
Aaron's holding a page there that's been sprayed with glow-in-the-dark paint. Now, if I hit it with red light, nothing happens. Okay, why? Because it's going to glow green. Okay, and so in order for that to happen, we have to give it more energy than is contained in red light or green light. So if you know your rainbow, red, orange, yellow, green, blue, violet, so we have to go past green. So we have to give it blue or violet light. And so even though those lasers are actually very bright, they don't give light of the right energy. And the difference between fluorescence and phosphorescence is, in the case of fluorescence, the light, we excite it with light and then the light is given off immediately. In the case of phosphorescence, there's a delay. And so now I've got, and so you can see it doesn't take very long, but there's still a delay there, right? It's still bright for a decent amount of time, right? Several seconds. Okay, so that's phosphorescence. That's how all your glow-in-the-dark stuff works. Okay. We're just doing...
Luminol clock next.
Oh, okay. Yeah, speaking of things that glow in the dark. Okay. Over here. So, glow sticks work with a chemical reaction that uses the principle of chemiluminescence. So instead of giving off energy as heat, they give off energy as light. And so what we've done here is we've set up a luminol clock reaction, which if you've ever seen CSI, you might know about luminol. It can be used to detect trace amounts of blood. We're not going to do that here. Instead, what we've done is we've created a clock reaction where these reactions will turn on depending on how concentrated the chemicals inside it are. 1, 2, 3. We'll see how long the last one takes. I put in a little too much. There it goes. There we go. Okay. All right, so that's a luminol reaction, and it's a clock reaction. Chemiluminescence is also a phenomenon that we see in the biological world. So different organisms will use chemiluminescence as a way to give off light. So like fireflies and deep sea organisms that need to create their own light to attract prey, for example, in the midnight zone in the ocean. Lighter, yeah. All right. And now comes the hottest reaction of the day. So this one you may have, if you're a fan of YouTube and looking at such science demonstrations, you may have seen. This is thermite. So this is a mixture of rust and aluminum metal. Okay. So aluminum metal you may recognize from such things as the spatula. And it's mixed into this flower pot with a little bit of sand, and now we just need to give it a bit of a kick, and the reaction will start. Now, we have to give it a bit of a kick because this mixture is actually stable. Okay, ready? 1, 2, 3. Now, how hot is that? Hot enough to melt the iron that was in there. So we actually got the oxygen to trade from being bonded to iron to being bonded to aluminum. And now we've got a whole bunch of molten iron in there. And you can see that that reaction is very, very fast, very, very hot. So over 2,500 degrees. Okay, and I don't know if you can pick it up on camera, probably not because it's too bright, but that is actually slowly flowing down the flower pot like a very slow lava flow. And with a temperature in the same range, so about 2,500 degrees. Now, what would you use that for? How about welding railroad tracks together? It's been used for that for a very, very long time. Okay, and our last demonstration also involves a little bit of fire. Okay, I need the blowtorch one more time. Okay. So if you like M&Ms, and let's face it, a lot of people do, I want to show you just how much energy is in one M&M. So this is a, we're going to use a peanut M&M. Okay, and as I mentioned earlier, there's oil in nuts, and there's a lot of energy in oil. More energy per gram than there is in a gram of sugar. We can access the energy from the sugar faster, but there's more energy in the oil overall. Okay, just like there's more energy in fats than in carbohydrates. Now, what I have in here in the cylinder here is a chemical called potassium chlorate. So this is an oxidizing agent, and we're going to digest an M&M just the same sort of way our body would use oxygen from air to break it down. But instead of doing it over, an hour or two, we're going to do it in about 30 seconds. Okay, and so just want to melt this, and then grab one M&M here.
Okay, great.
All right, there's a good one. Okay, and so this is, going to go to about 700 degrees when I put it in. So there's 13 calories in one peanut M&M. 13. So this is what 13 calories looks like. So right now it's about 700 degrees as it's burning through the chocolate. And now I'll give it a little boost. And now the temperature in there is over 1,000 degrees as it burns through the oil. Okay, and that only went through about half of that peanut. So I want you to remember this demonstration the next time you sit down and eat an entire bag of peanut M&Ms. Okay, so that's our show.
We have a few questions.
We have some questions, so let's deal with those. What are people asking?
So one of the reasons why we love doing this show is we're always learning, and people who come and see us and who watch online always has kind of some fun facts to share. So Paul Smith shared with us that the German physicist Hans Wilhelm Geiger is best known as inventor of the Geiger counter to measure radiation, and in 1908, Geiger introduced the first successful detector of individual alpha particles, which is what we were detecting today. So that's really cool. Thanks for sharing that, Paul. And then we had some questions about the liquid nitrogen. So one student asked, if your lungs were filled with liquid nitrogen, would they deflate like the balloon? So in principle, yes. but it would also kind of get really, really severe. It would destroy the tissue. It would just all be destroyed.
Yeah,
you wouldn't
you
live
would have
through
the
that.
worst case of frostbite imaginable.
Yeah.
And your lungs would actually have a hard time contracting because they're connected to all kinds of other supported tissue, right? So that they can open and close as we breathe.
Yeah.
So they would have that difficulty in contracting, and they're not really closed either, right?
That's right, yeah.
Unless you're swallowing something to your stomach, then
Yeah.
they're effectively closed.
Exactly.
Yeah.
Great, that's a great question.
Yeah.
And the second question is, would a human hand crumble in the nitrogen like the lettuce did? So the thing about humans is we have a lot of things inside us that the lettuce doesn't have. So we have bones, we have ligaments, we have other tissues. And so it would stay mostly together, but it would be solid, and parts of the outer skin might break off. But it would be severely, severely frostbite if we completely froze it. I have a feeling Jeff's going to do something crazy and show us a demo.
One of the interesting things about liquid nitrogen is that it actually doesn't take a lot of energy to make liquid nitrogen evaporate. So if you put something in there, a lot of the nitrogen evaporates really quickly. And so if I put my hand in quickly, don't ever try this at home. What happens is the liquid nitrogen around my hand evaporates and becomes nitrogen gas and warms up. So you don't actually really get serious damage. So I can actually put my hand in and scoop some out, and my hand's fine. Okay, but I'm not going to put it in there for more than like that second or so. Right?
Yeah.
Because then, yes, it certainly will freeze, and I will have the worst imaginable case of frostbite. And I've already broken 8 of my 10 fingers and thumbs, and so I have no desire to break any more.
Yeah, we don't need to break Jeff anymore.
Yeah.
So another question having to do with the liquid nitrogen. Why did they not use something other than liquid nitrogen for the lettuce? So that's a great question. We could have froze the lettuce another way. If you put lettuce in your freezer, it'll wilt like that as well. The liquid nitrogen, though, because it's so cold, it can do something called flash freezing, where it freezes it almost immediately. And that can affect the lettuce a little bit differently. So we can shatter it, we can do all these cool things. Whereas if you put a piece of lettuce, you can try it at home, try out the experiment, let us know. You can tweet us at Carleton Science or at Carleton Chemistry online and show us the results of your experiment. But we like to use liquid nitrogen because it's fun to play with, and it's something you don't always get to see at home.
Yeah, and flash freezing is also something that is becoming increasingly common in the food industry.
Oh yeah, gastrometry or...
well, not just that, but like if you flash freeze fish or something as opposed to slow freezing it, it will thaw faster.
Yes.
When you want to cook it, right? And so we usually, if something's frozen, we usually want to thaw it before we cook it.
And that reminds me, there's lots of examples that you can actually eat of freeze-dried things. So there's astronauts ice cream, which is freeze-dried slightly a different way, takes the water out. Yeah. There's candy that's freeze-dried, but they also use liquid nitrogen in cooking to make ice cream. So if you come to our show in person, you might in the future get some sampled ice cream from liquid nitrogen, which is cool. So one question, is the radiation actually green? So the light that's coming off is green. That's why, well, we're seeing it as a green wavelength. And so we know, depending on how much you've learned so far, you might understand how green light is produced in different ways. But that radiation is green. If you're talking about the radioactivity, that molecule happens to be green, but they're not always green. You can have radioactivity in different colors as well. And then the last question here we have is for you, Jeff. So how much oil can a pecan hold?
I think a lot of nuts are in the range of about 40% of the weight, 40 to 50%, maybe, depending on the nut. The weight of it is oil, and then the remainder is proteins, carbohydrates, and other things, waxes, that kind of thing.
Cool.
That we can eat.
Great. So that wraps up our questions.
Okay.
and wraps up the show. Do you want to do the
All
thank
right.
yous?
Yeah, so I guess what remains is for us to say thank you to everybody who helped us put on the show. Larry and Alex and Jamie and Jared, thank you. I was like blanking, it's a J name. It's a different person from yesterday. Sarah, all our staff in stores, Daniel's son, one of our technologists here, and a whole ton of other people. It's probably about 50 people that help us put on
Faculty
this
of
show.
Science helps us.
Yeah, and Let's Talk Science has done a great job of helping us promote the show, so thank you to Sue and the local chapter of Let's Talk Science, and everybody else who's been part of the show. A big thank you to them. And so, yeah, that's our show. So thanks everybody for coming.